In this video, we're going to talk about discovering or deriving the area formula for a rectangle. Now remember, in our last video we talked about how, among other things, we can think of area as being trying to determine how many little square tiles will fit on a region. So technically speaking, the rectangle itself, being just the border of this, doesn't really have an area. It's the interior of the rectangle, which is this purple region, that actually has an area. But we often say the area of a rectangle, meaning the area of its interior. Now, notice that if we have 3 rows and 6 columns of squares, we can think of this as groups, and each row being grouped, so we can think of this as 3 groups of 6 added together. Well, that's exactly what's meant by multiplication. So we see that this is a model that we would use for multiplication, probably back in elementary school when we first start learning multiplication. And of course, if you can go 3 times 6 is 18, or 6 plus 6 plus 6, or you can just count them all, but you get 18 anyway you go, which is 18 square centimeters. And this sketch, like most sketches, is dynamic, so now there are only 12. Now let's look at another example. Here's an example here where we have the height is 3.5 and the width is 4.5, and we can see that we have the 3 times the 4 is 12 total squares here, but these little pieces going across here are half squares. So these two together make another 1. There makes another 1. So let's see, there's 12, 13, 14. And another one here is 15. And there's a half. And where this meets is a half times a half is a fourth for that. So we get a total of 15.75. So no matter what we have for a rectangle here, no matter sort of which direction it's going, for a general rectangle, as we look at this one here, for example, if we take the two sides that are adjacent to each other, they're perpendicular to each other, call one of those the width and the other one the length, the area then is going to be the width times the length. Or if you call one of those the base and the other one the height, then we have base times height. And so this one I can adjust and get any value, not just integer values. And it really doesn't matter which direction I turn it. It depends on the size of these things. And so now we see that the general formula for an area of a rectangle is base times height. Now let's talk about a parallelogram. How can we find an area of a parallelogram? And one of the key things to do is, if we can take this and slice off a piece of it and move it over, notice that we form a rectangle and we've kept the total area the same. This trapezoid shape, right trapezoid here, they share in common. And if we could just show that that triangle and that triangle are the same, then they would be the same area. And here's the actual proof of it, okay, where we start by pulling this down, and we pull this over here and figure out both of those areas. We just need to show that these two triangles are congruent. Well, one thing we know about parallelograms is opposite sides are congruent as well as being parallel. So those two sides are the same. These are both right angles. And then we also have this angle here at C and this angle at B are congruent. So by angle, angle, side, the two triangles are congruent, and therefore they must have the same areas. So if we just cut this off and move it over here, we get the same thing. So this must have the same area as the rectangle. And let's hide the triangles now. And but let's show the rectangle that I'm talking about. If you take that rectangle, it has the same area. And it really doesn't matter what I do with this parallelogram. It might look like this, for example, or it might look like this one here. I can change its size and shape. But wherever it is, there's always a rectangle that has the same area. And so all we have to do is just, of course we know the area of that rectangle is base times height. Okay, so we know that that base is down there B, and there's the height H right there, and we know base times height will give you the area of that rectangle, so that must be the area of the parallelogram. So if we hide that, what we just need to do is find the base, find the height. So there's the height there. So what is the height? Whichever side is going to be the base, the height is the perpendicular distance to the opposite side. Okay, so there's the base and there's the height. And that is, then the formula, of course, then is just base times height, and you can see what it is for this particular one. So that shows you how we can start with the area of a rectangle and use that formula to find the area of a parallelogram. Now, in trigonometry, we're going to be dealing a lot with measuring triangles, so let's look at how we can come up with an area formula for a triangle. Well, one way we can do with it is to construct a parallelogram. And what we do is we take one side, we'll call it the base, B, down here. Construct the altitude, which is take the opposite side and draw up a perpendicular. Now this may be inside, this may intersect down here inside the triangle, or if the angles are the right way, it may intersect, it may come down here outside. So there's the base and the height. Okay, but now let's look at the parallelogram I want to construct. So I'm going to basically extend this triangle out till I make a parallelogram. So what I do is I just take the base side, construct a line parallel to that there, and then take the side over here, take this other point B and construct a parallel to that. Where those two intersect, we'll call that point D, and now we've got a parallelogram from A to C to D to B. Now we know the area of that parallelogram is base times height. But what I want to show is that in fact those two triangles are actually congruent to each other, and one way we can see it is they share this side. We know in a parallelogram that opposite sides are parallel and, well, actually let's just start with the fact that they're parallel. This angle down here is congruent to the one up here, so angle DCB is congruent to angle ABC by the Z property, kind of an upside down Z there. Opposite, alternate interior angles, when a transversal intersects a pair of parallel lines, the alternate interior angles are congruent. That's the Z property. So this angle right here and this one down here are congruent. And let's see, we also know that opposite angles are congruent here. So well, let's just use the Z property again here. We get a Z going this way. These two sides are parallel. So the top and bottom being parallel is what makes the angles, this little angle up here at C and the little angle at B, congruent. But we also have parallels here and here, and so then we get a Z going like this. Okay, and that makes the angle here, the bigger angle at B and the bigger angle at C, congruent. Well, that gives us enough to get angle, side, angle. Of course, this side right here is congruent to itself. So now we have angle, side, angle. Angle, side, angle. So by the angle, side, angle theorem, these two triangles are congruent to each other. And so these two areas are the same. Well, that means each one of them is 1/2 the area of the parallelogram. So there's always a, so I could hide, well, let me show the parallelogram. And there's always a rectangle that has the same area as the parallelogram there. So we get the same area on that parallelogram, on that rectangle. So if I hide the rectangle, I could look at it this way. Here's another way to see this. If I were to draw the altitude right there, you can see a little rectangle here, and you can see this little triangle is half of that rectangle. And this triangle right here, this right triangle, the bigger right triangle, is half of the other rectangle. So overall, the triangle we start with is half of the other one. You have to be a little bit careful doing this as a proof, because you have to start looking at all the cases. For example, looking at this case is a little bit harder to see, but it's still true that we get half of this area is the same as half of that one. When it's inside here, it's pretty easy to see. Outside, it takes a little bit more work, but we can see it as well there. So either way we go, that is half there. So, bottom line, what's the formula for the area of a triangle? It's going to be half the formula for area of a parallelogram. So we take our base here and our height here, and we multiply those together and then take 1/2 times that. So the area of a triangle is 1/2 base times height. Now, if you happen to have a right angle here, then we're just multiplying 2 of the side lengths. So let's see, let me change the letters here. Let's change this one to A. Now I want to leave it. I want to make it B. Excuse me. Okay. And I want to, because I want this little b to be opposite. This is sort of the way we normally label these things. And we'll make this one A. So this side over here is A, and this side here is C. Now, if you have a right angle at C, then A and H are the same. So I'll kind of label some of these. This is little a, and this is C. So notice that if it's a right angle at C, A and H are the same, and so it just becomes 1/2 A times B. But if it's not a right angle at C, then you need to compute what H is. And so there is the formula for area of a triangle. And that's going to be useful when we start solving triangles a little bit later on down the line.